Okay.
Good afternoon, everybody. My name is Pavel Ostrovsky, and I'm really surprised by how many people are here in the audience. I hope this will stay approximately the same through the whole course. And also, I just recently learned that, actually I already forgot, what's the name of the course? Who knows? Quantum transport and topology, exactly. So what I will start with will be about transport, but for today it still will not be quantum and there will be no topology. It will be just transport. It will eventually become quantum transport by the next lecture, and topology will appear much later, hopefully. Yeah, and also I'm not sure what your background is. I mean, you're probably people from different branches of physics. So if I say something that you do not understand, please interrupt me at any moment with any questions. Don't be shy. In the worst case, I will also not know the answer. But the goal is that you understand something from these lectures. So if you do not understand what I'm saying, just stop me immediately. Great. And so what is this whole course about? Is mostly about how electrons propagate in metals and what different effects can happen in such a system. And the very first topic that we will discuss, can you hear me like this? The very first topic is actually classical diffusion. Classical diffusion, it's the very, very simple description of how something propagates in a disordered medium, and I will first tell you some very basic facts about diffusion, and then later today, hopefully, we will see how you can use quantum mechanics to describe this classical diffusion. So mechanics would be quantum, the result will be still classical. And yeah, I hope everybody knows what diffusion is. It's when one material somehow, some small particles propagate in a medium of other particles, and this classical diffusion is described with a quantity which is called density. Density is usually called n, is a function of position and time. Position is a vector, time is a number. So you can have, for example, it can be anything, but in my case density will be mostly density of electrons. You have a piece of metal like this. This is wood, sorry. Like that one. And you have some electrons inside and they can move freely, so you have some concentration of these electrons at a particular point, at a particular moment of time. And the first thing that you can say about this density is that it's conserved. When something moves from one point to a different point, you get more density there and less density in the original position. So the first thing that's called the continuity, which is the following statement. The change of density with time plus the divergence of current equals 0. I believe it's plus there, right? Yep. So current, I forgot to mention, we have a density which tells us how many particles we have per unit volume in a given point, and we have a current which tells us how these particles flow, and this is a vector, J, which also can depend on position and time. And these two things, they are related by the continuity equation. If in some volume you have a certain density, it changes with time. If you have current, it also changes the density with time, and the sum of these two things should be 0 because the total number of these particles is conserved. Is it clear? Clear?
You can add a source if there is a difference.
Yeah, so in a closed system without any external sources or sinks, this should be like this. Otherwise, yeah, you can have something different there. So this is the first thing, and the second thing, which is called, actually it's called Fick's law. Fick is the last name. Fick's law is another relation between current and density, and this relation tells us that the current is inversely proportional with, is proportional but with a minus sign to the gradient of density. If in some part you have more density and some other part you have less density, then it will flow from where it's more to where it's less, and the coefficient here is called the diffusion constant. Actually, this is a very simple relation, and I only recently learned that it has a name. I mean, we all know that it should be like this. So D, this D here, is the diffusion constant. Which is not always a constant, it's just a name. So this tells us, once again, if we have more particles here and less particles there, and they diffuse, then there will be a current that flows from the place with larger density to the place with lower density. So these two, if you like, this is just a simple linearized version. If you have some small variations of density, you will have some small current, and these two things should be proportional, and D is just a coefficient. So if we now combine these two equations, we take the current from here and insert it here, we will have a single equation which looks like this, and this is called the diffusion equation. So once again, if you have density which is somehow distributed non-uniformly in space and you let it flow according to the diffusion equation, it will change with time like this, and actually it will lead to equilibration. So density is trying to become equal in different places. This is the diffusion equation. It's a very simple equation. There is a lot of theory about this. It's the same. It's exactly the same equation for temperature equilibration. For instance, if n is not the density but it's the local temperature, you will have a similar equation, and you will have, instead of diffusion constant here, the thermal conductivity. Or there are many other processes that are described with this equation. So in our context, we will think of it as a diffusion equation, and it's a very simple equation for a single scalar object, a linear equation. It's first order in n. It is uniform. It has 0 on the right-hand side, and it has some derivatives in time and in real space. So, how to solve this equation?
Is if D is spatially independent?
Yeah, D is a constant. You see, it's a constant.
And you do Fourier transform and the Laplace transform.
Yeah, this is exactly correct. So the object that is usually studied in physics, in all possible branches of physics, is something that is called a propagator. Propagator. Propagator is, we will call it also with the letter D, but in some different font, curly D, which is also a function of position and time. Propagator is the solution to this equation, the time derivative minus D times the, this is called Laplace operator, acting on this object D of R and T equals the delta function of R and the delta function of T. This is true for any linear equation. If you have a linear equation with 0 on the right-hand side, you can define a propagator of this equation, which is the solution of the same equation where this 0 is replaced with a delta function. In our case, it's time and space, so it should be a delta function of time and space. And once we solve this equation with the delta function on the right-hand side, we can express any solution with any initial conditions through this object.
Well, any of those which have the same boundary conditions as the green function.
Yeah, in my case, it's just in the infinite space, so there are no real boundaries. But you're right, yeah, in a closed system, you should solve. Boundary conditions are, in a sense, a part of this operator. So this is an operator which I didn't specify any boundary conditions, but if they are specified, they are the same here and here.
Just saying that you can have multiple different green functions technically.
Yeah, that's true. But also, formally, they are green functions of different operators, because boundary conditions are a part of the definition. Yeah. Okay, so to solve this equation, as was already suggested, we should do a Fourier transform, and in physical terms, it means we go from the real space and real time representation to a momentum and frequency representation. So I will write it explicitly, at least once. We write this object D of R and T as an integral over all possible momenta, Q. I will explain a bit later, divided by 2 pi, and over time, over frequency, divided by 2 pi, of a new object which depends on Q and omega, and with the exponential factor IQR minus I omega t. So this is a Fourier transform. We have a function in real space and time, we have a function in momentum and frequency, and they are related by a Fourier transform like this. And in principle, we will study a d-dimensional case when this real space can be 1, 2, or 3 dimensional. So this momentum q and this real space vector r is either a vector with 1, 2, or 3 components. So I write this for all cases at once. We have d-dimensional q integral, and it's divided here by 2 pi to the power d. So d is 1, 2, or 3. In some cases, it can be a different number, but 1, 2, or 3 is enough for now. So if we do such a thing, then we ask a question, what happens when we take a time derivative of this? Time derivative acts on the exponential. It multiplies the whole thing with minus I omega. If we apply a gradient in real space, gradient acts on R, which is only here. It multiplies by I times Q. So after this Fourier transform, we replace this equation by minus I omega plus dq squared acting on d of q and omega. And what should we do with the delta function? So this is the Fourier transform of the left-hand side. And in the right-hand side, we need a Fourier transform of the delta function. which is just the number 1. So if we do a Fourier transform, this is actually true for any differential equation with constant coefficients, linear differential equation. The Fourier transform transforms this equation into an algebraic equation. So now it's just something times something equals 1. It's an algebraic equation, no derivatives anymore. So we have a result, d of q and omega equals 1 divided by dq squared minus I omega. And this will be a very important object which we will use in all the lectures from today till the very end. This object is called diffuson, or a propagator of diffusion equation. It's called like this, you know, these Greek names like particle, diffuson, like electron, but for a different thing. And it's most simple in a momentum and frequency representation, but we can also transform it back to real space and see how the solution of this equation looks in the real space and real time. It's no problem, it's just that in this q and omega form, it's the simplest form. It's the simplest form for this thing. Okay, so there is a very important property for this object, namely it diverges, becomes infinite, diverges if you set q equals 0 and omega equals 0. You see, you just have 0 in the denominator, it diverges. This divergence is called a diffusion pole. For some reason, I don't know. Diffusion pole, it's like, you know, like the poles in the complex functions. When you have 1 over z, it's a pole. So it's a diffusion pole, and the existence of this diffusion pole has a physical meaning. This pole appears exactly due to the conservation of the number of particles. So this equation, the total number of particles under diffusion is conserved, and this conservation is the reason why the diffusion diverges. Conservation of the total density, if you like. Total and actually this happens many times in different contexts. Whenever you have certain conservation law, you have a certain divergence in a corresponding propagator. We will see it later, many other examples of this. So right now, we don't have to do anything with it. We just derived it. We see that it diverges. So we are happy. There's nothing to do. So this is property number 1. Property number 2 will be a bit later. Yeah.
Questions first. The pole is only divergence at q goes to 0 and omega goes to 0.
Both go into 0. Yeah.
So it is not like when omega equals to just t squared.
No. It's just when both go to 0.
Second question: is there any visual simple way to see that this is all corresponding section? So continuity equation.
Not exactly to continuity equation, rather to conservation of the total density. So you take this equation, or this one, yeah, you can take an integral over the whole space, and you will have here the time derivative of the total density, and this one will be 0 because it's a gradient, and you take the integral over the whole space, and you will see that the time derivative of the total density is 0. Then the question is, then you have this 1 divided by 0, right?
Yeah.
It's not the exact derivation of this pole, but it's some kind of expression. Okay, so as I promised, or as I just suggested, we can also write this object back in the real and space and real time, and we will do this right now. So what we will do right now, we will convert omega to time. We do a Fourier transform back from frequency to time according to this integral here. So what is the this diffusion propagator as a function of q and time? It's the integral over all frequencies over 2 pi, exponent of minus I omega t, divided by dq squared minus I omega. With time. Does anybody know how to compute such an integral? No?
This one is probably with contours.
Yeah.
Imaginary version.
Yeah, so it's an integral over omega, which enters only in 2 places. There is an exponent and there is omega in the denominator. So the easiest way is to complete the integration contour. So we integrate along the real axis. This is the complex plane of omega. We integrate along the real axis. And there is a single pole, which is 0 of the denominator, when omega equals how much?
You have to add either plus or minus I or so.
Minus I dq squared is the only singular point of this expression. It's right here. When omega equals minus I dq squared, minus I times minus I is minus, so it's 0. So there are two cases. Case number 1, if time is negative, t is negative, it means that this exponential factor grows in the lower half plane when omega has negative imaginary part and decays in the upper half plane. So we can close the integration contour in the upper half plane when t is negative, but there is no singularity here. So for negative time, it is just 0. And when time is positive, it's minus I omega positive number. We close the contour in the lower half plane, and we pick up a residue at this point. And since we close in the lower half plane, we should write minus 2 pi I, the value of the residue. And if you do all the bookkeeping, 2 pi will cancel to this 2 pi, minus I will cancel this minus I, and what is left is just the exponential. So residue is 1, minus 2 pi I residue is 1, and the answer is just this exponential, which is, you substitute this instead of omega, and you get minus dq squared t. That's all. So, as I promised, there is a second important thing about this diffusion, this propagator, namely, it vanishes, it is 0, it vanishes when time is negative. Or another statement. It's analytic, which means has no singularities in the upper half plane of complex parameter omega. It's analytic for imaginary part of omega larger than 0. These two statements are actually equivalent. Whenever you have a function that is analytic in the upper half plane, and you do Fourier transform of this function, you will always find that it is 0 for negative argument. And vice versa, if you have a function which is identically 0 at negative argument, you do a Fourier transform, you get a function which is analytic in the upper half plane. These two things are equivalent, and they both have a single name. This property is called that diffusion is our object is retarded. So we have a propagator of the diffusion equation, which is retarded, what does it mean? Retarded means it's 0 at negative t, so something happens only at positive t. You inject a particle, this delta function, now the meaning, this delta function on the right-hand side means that you inject a single particle at the origin at r equals 0, at the time t equals 0. Before this, before time equals 0, there were no particles. There was 0 here, there was nothing, d was exactly 0. So for all negative times it was 0. Then you injected a particle, and then this particle starts to diffuse. At positive times, it does something according to this exponential. So retardation means that this diffusion equation tells you that something happens only after something was inserted there. So the response, this diffusive response, comes in time later than what it responds to. So you have some perturbation, and then at a later time you have a result of this perturbation. This object is retarded, and so it just vanishes at negative time, or it's analytic for omega in the upper half plane. This is the same thing. Now, let us do the next step. I can even draw this as a plot. So this is time, and this is d. This is our diffusion. At negative time, it is 0. There's nothing here. And at positive time, it is this exponential. So it looks like this. Just exponentially decays, and there is a jump at t equals 0. You can fix any value of q. I don't know which one you like. But for all values of q, it will look like this. So this is exactly what it means to be retarded. 0 negative time, and then some response to what happened. So here, when we kick the system with the delta function, we have a jump, then this jump dissolves. Okay.
I'm just asking, when we do this contour integration, we get 2 pi I times the residual.
Yep.
Where does the I go?
So this integral, we write minus 2 pi I times residue. Then we have 1 over 2 pi here. And if you want to get a residue of this thing, you should represent it in the form omega minus the position of the pole. So you have to take this minus I outside. But minus I here, let me put it like this. And then it will be a residue of 1 over omega minus I dq squared. Present it like this. So the residue of this thing is 1. And then these two things just cancel out. Okay, any other questions? Well, great. So what we do next,
In the case of the diffusion, there is actually just one propagator, because you can't afford this whole.
actually, there is only this propagator. Yeah, it's true. So what we do next, we do another Fourier transform to find how this d actually depends on position and time. So we already did it for time. Now we will, I don't know where is the best. Can you move this?
Yes, there's a button somewhere there. To the left.
On
the left.
white box.
In the
This is the wrong one. Yeah.
in the box.
Oh, there are many buttons here. So let us compute the object the same object, which depends now on real position and real time. So we take this one which we already found, and first we say that this is a theta function of time. This is called a Heaviside function. It's just 0 negative argument and 1 positive argument times the momentum integral. Now we do a momentum integration, dq over 2 pi power d, exponent of I q r. This is just this part here. And then that exponent, which we have from the diffusion constant, so I will put it right here, minus dq squared d. This is a new integral that we have to calculate. And so this theta of t is just a prefactor, which is not very complicated. So how to calculate this integral? We will have a special course in mathematics.
Because otherwise you can't really
This,
say. Or is it like a general expression?
this is called a Gaussian integral. Just in case. It's the exponent of some quadratic expression. You have q squared and the linear term in q. So it's just a Gaussian integral. And in order to calculate this, we will do what is called complete the square. So we will write exponent minus d time, and then I will write q plus some constant squared. Q, which constant? Minus IR over minus IR over 2d t squared. So if you open this square, you have minus dtq squared plus IQR 2 dt, yeah. So you have these two terms correctly, and then the last term is plus r squared over 4 dt, so I should have to subtract it, minus r squared over 4 dt. Right? Okay, so what we do, we have a q integral, and we have q plus a constant here. We can shift the integration variable by a constant, so we just drop this out. And this is just a number which does not depend on q. We can take it out of the integral. So we will have the following result. Result equals theta function of t times exponent of minus r squared divided by 4 dt, and then some number which is the integral of this exponential. Yeah. So if there is no d dimensions here, this is called a Poisson integral. Poisson integral of exponent of minus x squared is the square root of pi divided by 2 pi, means 2 square root of pi divided by the square root of dt, because we have to rescale our variable, which means the square root of 4 pi dt. 4 pi dt. And it should be a square root. Square root is power 1/2. But we have d such integrals. So the power is d half. This is the answer. And I have some notes to check. Yeah. And this is what is actually written in most textbooks about this thermal diffusion, or usual diffusion equation. You have a delta function at the moment t equals 0. It's a very high peak, which is infinitely narrow, and then with time it spreads in real space and becomes a Gaussian function. It's a Gaussian function. Yeah, it's like this. It's a Gaussian function which with time gets broader and broader, or at very small time it's very narrow. So this is what happens. You have a narrow peak, then with time it diffuses from the origin. This is, sorry, this is r, this is point 0, and these are the curves with different values of time. It's for positive time. For negative time, you have nothing. So this is how the diffusion propagator or diffusion looks in real space and real time. And am I supposed to give any homework in these lectures? Who wants homework? Okay, so personal homework for you. Or for anybody who wants to participate. Homework. Sorry. Homework. Find the diffusion propagator and in real space and frequency. So we have this object with momentum and frequency, with momentum and time, with real space and time. So the only one missing, which we did not find, is the real space and frequency. And I didn't show it here with a good purpose, because it's not a simple thing. That's why it's homework. Why you would do simple things at home, right? So just to make the life easier, homework contains 3 parts. Find d of r omega, part number 1, for d equals 1 in a one-dimensional system. This is an easy part. Part number 2, which is more complicated, but still doable. Do the same thing for d equals 3 in 3 dimensions. And finally, part number 3, which is the most challenging, do it for d equals 2. And the part number 4 with 2 stars, do it for any d without specifying it. Actually, as you can probably tell, I'm not Slovenian. I have no idea what's the what system is used here for giving marks to students. But from where I'm from, mark 5 is the best, then 4 is below, 3 is even below, and 2 is the worst one. So let's say this is to get 3, this is to get 4, and this is to get 5. But I'm sure it's completely different here. So okay, so we are talking for how many? For 45 minutes, right? 40 minutes. But we started a bit later. Shall we do a break or not? I have shown about a quarter of what I wanted to show today. So if we do a break, it will not spoil anything. I mean, we have no chance to complete it anyway. Oh, well, no, let's do without break. I will try to spare some time at the end. Okay, great. So this was all I wanted you to know or to remember about classical diffusion. Now we'll do something more physical, less mathematical. Where is it here? So the next topic, which is related to this classical diffusion, is the following. Imagine you have now a real metal, and we are talking about diffusion of electrons inside a metal. So this for now was about any diffusion. You can even apply this to thermal diffusion, for example, to diffusion of whatever other scalar thing. Now, real electrons in real metals, this is metal, right? There is a very important thing that is called Einstein relation. Einstein relation, which applies exactly to the diffusion of electrons in metal. And this is what it means. Just imagine we have a piece of metal and we have some electron density inside. The electrons are distributed inside, they have some density, and these electrons have different densities and different parts. Then there is a diffusion, and the electrons try to come from the part where they are more dense to the part where they are less dense. So we have a current, which equals, we have this equation, I just raised it, minus d gradient of n. Now this is a current of density. And when we are talking about electrons, we usually are talking about electric current because each electron is charged. So when you have flow of electrons, it means not just the density flow, it also means the charge flow, the electric current. So if you just multiply it with the electron charge, this will be now an electric current. And then there is another way how you can induce electric current in a metal. You take a piece of metal, you plug it into the outlet here, and you have a current inside. So you can apply electric field. If you apply electric field to a piece of metal, there is a force acting on electrons which induces the current. And if we have a metal with some non-uniform density, and we additionally apply the electric field, we can add to this current another contribution, which is sigma times electric field. Sigma is the conductivity. Yeah, current is sigma times electric field. This is called the Ohm's law. Current is proportional to electric field. The coefficient is the conductivity. So if in a piece of metal we have simultaneously non-uniform density, some gradient, and some applied electric field, we have the current, which is the sum of these two contributions. Now imagine, as Einstein did 120 years ago, imagine that these two things exactly compensate each other. We apply some electric field, current flows, it induces the gradient of density such that it compensates the electric field and the total current becomes zero. Zero equals zero. This is our assumption. We assume that the total current is zero. It's some equilibrium situation when the effect of electric field is compensated by this gradient of density. This is an equilibrium, current is zero, nothing changes with time, everything stays where it is. So you take one other thing. In this expression, where we have the gradient of density, if you have a piece of metal and you add more electrons or remove some electrons, you change the density, but you need some energy to do this. To extract an electron or to add an electron to something, you need certain energy, and this energy in thermodynamics is called the chemical potential. So when you change density, when you add particles or remove particles, you need an energy which is called the chemical potential. So this gradient of n can be written as the derivative of the chemical potential with, derivative of n of the density with respect to chemical potential, right? Yeah, times the gradient of mu. Sorry, I will explain it a little bit better later today. Just for now, when you let me put it differently. When you change the concentration of particles, you also change the chemical potential. And and these two things are related. Density is the function of the chemical potential. So when density changes from here to there, chemical potential also changes proportionally. This is just a number. And this number here, it has a name. It's called nu, the Greek letter nu, and it's called density of states. Density of states. This is a standard thing. It exists in any metal and even non-metals, in any more or less material. You can define what the density of states is, and it's just the derivative of the electron density for metals with respect to chemical potential. So I just want to replace this gradient of n with gradient of chemical potential. This just one is the function of the other. Once again, just in 10 minutes, I will talk more about this topic and it will be clear how this happens. Then, as I already mentioned, current is zero. The system actually is in the equilibrium. So, what do we know from thermodynamics about the systems in the equilibrium? Actually, I don't know anything, but I can take the textbook, look inside, and it tells me that in an equilibrium system, there should be a certain quantity constant along the whole system, and this certain quantity is called electrochemical potential. Electrochemical potential. This mu is chemical potential. Electrochemical potential is the sum of electric potential and chemical potential. Electric potential phi times electron charge plus mu. This is the electrochemical potential. I can try to explain it without equations. So chemical potential, mu, is, as I said, is the energy you need to add an electron to a material. Because all electrons inside are somehow chemically bound to the nucleus and to one another. So this is the energy you need to add an electron to satisfy all the chemistry of the material. Electric potential is also an energy you need to add an electron to a particular point. It can even happen in vacuum. If you have some electric field, it has an electric potential, and this potential tells you what is the energy of electron at a given point. So E times phi is the electric energy, and mu is the chemical energy. And the sum of them, the electrochemical potential, should be the same in every point of your object, of your material, for it to be in the equilibrium. If you move electron from here to there, you can lose some chemical energy and some electric energy, and you can gain some chemical energy and electrical energy in another place. So if it's not a constant, it's not in equilibrium. Electrons will really move to make this thing smaller. So it should be, in any equilibrium state, this combination should be constant, should take the same value in all points of your material. And I forgot to say that electric field here is actually the gradient of electric potential, but this is easy. So we can describe the equilibrium state in two different ways. We can say that the diffusion current is fully compensated with electrical current due to electric field, or we can replace the gradient of n by the gradient of chemical potential. We can replace electric field by the gradient of electric potential, and then we should say that this combination should be constant, which means its gradient should be 0. So this is equation number 1. And this is an equivalent way to say the same thing. Minus E times D times nu times gradient mu plus sigma times gradient phi equals 0. This is the equation number 2. These are two different ways to say that the system is in the equilibrium. Its electrochemical potential is 0, or the two contributions to the current compensate each other. And one contribution to the current is written in terms of the diffusion constant, and the other one in terms of the electrical conductivity. Now I will check that I have written everything correctly. It's minus here. I forgot my school physics. Electric field is the minus gradient of phi. So it's minus. So we can do whatever we like with this equation. For example, we can take gradient of mu from here and substitute it in here. Sigma times gradient of phi equals minus E d nu, gradient of mu, equals minus E d nu. Gradient of mu is minus E gradient phi. Sigma times gradient phi equals this times gradient phi, and by cancelling gradient of phi, we have following identity. Sigma equals E squared, density of states, diffusion constant. This is called the Einstein relation. the relation between electrical conductivity and diffusion constant for electrons in metal. The larger is the diffusion constant, the faster electrons move. The larger is the electron density, sorry, not electron, the density of states, the more available states you have. The product of these two means, so the more you have either of this, the better is the conductivity of the metal, and this is the exact relation. There is no, it's derived, of course, from a very simple, relatively simple classical equations. It remains correct in the quantum mechanical limit as well. So it's so general, it's just the exact identity. If you like, this is a definition of conductivity, or the definition of the density of state. So you can use this as one of the basic identities for this theory. Yeah.
So it's called Einstein's identity. What is called in this form?
This will be the topic of the next 10 minutes. I will.
So Einstein derived it first, and Drude came and
No, Drude was before Einstein,
called Einstein.
because this was derived by Einstein. You will see, just in a minute, or in 10 minutes.
There is many Einstein relations.
No, this is not the only one I know.
Which is also called Einstein relation, which relates the temperature coefficient, right? So
Which one?
it's like if you have a, similarly you can express
Viscosity and diffusion.
So for example, if you have a temperature, right?
Ah, okay, right, yeah, but it's well, you're right. But it's the same idea behind it. I mean, you can consider the equilibrium not between gradient of n and electric field, but between some gravitational field, yeah, and whatever gradient of, I don't know what.
And that one has also different names.
Okay, so this is the Einstein relation for electric conductivity. It is derived in a very general terms without assuming anything about the metal itself. What is metal? I have no idea. Metal is just a black box with some electrons inside. These electrons can diffuse. These electrons have charge and they can conduct current, so there is an Ohm's law. And also there is some strange object which is called the density of states, which means that these electrons, the concentration of these electrons depends on another strange object, which is chemical potential. So right now I will illustrate this whole thing, giving you a concrete example, the very simple model, what metal is, what electrons do, and how this whole thing appears. And this will be what Drude did, actually. So the history is the same. Drude did it for some simple, particular model, and Stein derived it as a general identity applicable to anything.
So if J is not equal to 0, then it doesn't hold?
No, it's not about J equal to 0, it's about, so you will see. Right, it's just, so the simplest, very basic model of a metal. What is metal and what electrons actually do in a metal? Metal, we can think of it as just a box with walls, and with some electrons inside, they just fly freely back and forth. And the electrons that fly have a certain energy. Sorry, I should say it's what I'm talking as a model of metal. So electrons inside a metal can fly as free particles. This is our model. Of course, in reality, they don't do this. But just for a moment, imagine they are free particles and they have the energy, which is, as for any free particles, is a momentum squared divided by 2 times the mass. This is what free particles of the mass M2. This is momentum. This is energy. Everybody knows this, and we can plot this complicated function. This is energy. This is momentum. And this is a parabola. But these electrons, they are free. They do whatever they like. They just fly freely. But they're still fermions, which means they cannot occupy the same state. Two electrons cannot occupy the same state. So different electrons are forced to have different values of momentum. They cannot have the same momentum. And if we have a certain number of electrons inside, they will occupy all the states with different momenta up to a certain energy level. They don't want to have they want to minimize the energy, so they will start occupying from the bottom, and they will end at some level. It's my poor way to draw. This is not just a parabola, it's like a three-dimensional thing or two-dimensional. So they will occupy all states up to a certain energy level, and this energy level has a name. It's called Fermi energy. Fermi energy. This is the simplest model, so it's zero temperature. Nothing happens. We have occupied states at these energies and empty states above this. This Fermi energy, in this simplified model, has another name. It's called chemical potential. In this simplified model, it's not correct in general, but then it's called either E Fermi or mu, whatever you like. Now, why is this chemical potential? Exactly because, as I explained earlier, chemical potential is the energy you need to add an extra electron to the system. If you take an electron and try to insert it inside this metal, all states here are occupied, so you need an energy at least of this magnitude to put this electron on top, to fill the next state. So this is, by definition, the chemical potential. Now we also have, let me put it this way, chemical potential equals P Fermi squared divided by 2m. P Fermi is the Fermi momentum, is the radius of this disk. So electrons occupy all the states with momentum less or equal to Fermi momentum, and with energies from 0 up to Fermi energy, and the Fermi energy and the Fermi momentum are related by this relation. It's as easy as this. So chemical potential, Fermi momentum are related like this. Now, if you ask what is the electron density in this metal, how many electrons per unit volume do we have there? The answer is easy, just compute how many states are occupied, and this is your electron density. Electron density, M, is an integral over all momenta, d-dimensional, we have d dimensions, divided by 2 pi power d from 0 up to Fermi momentum. And there is a mistake in this equation. Actually, it's times 2, because electrons have 2 spins, so you can put 2 electrons in each state. And I will not ask you what this integral is. It's very complicated.
Oh yeah, in D dimensions.
In d dimensions. In any specific dimensions, it's,
Volume of the sphere.
yeah, it's just the volume of the sphere. But I don't need it. The only thing I need from this is that this density is proportional to the Fermi momentum power d. So, two relations. Mu is related to the Fermi momentum, like this, and the density is related to Fermi momentum, like this. And actually, if you start adding more electrons, you will fill more states, your density grows, and the chemical potential also grows. This is exactly what was meant by the density of states. This derivative, how density depends on the chemical potential, it just tells you how steep this curve is here. So you add electrons, if you like, the density is the volume that you fill, and the chemical potential, the change in the chemical potential is just the change of the height. So the larger is the surface, the more density of states you have. The smaller this thing is, the less density of states. So why do I need these two relations? Actually, I will show it a bit later. I will introduce one other part of this model of a metal. So far it was just a free electron gas. Electrons just fly freely the way they like. And now I will introduce also some obstacles. They will scatter at something. So this is usually called impurities. In any metal, you have impurities. So if electron has a certain momentum, velocity, it propagates in a certain direction, it encounters an impurity, scatters, it can change its momentum and fly in different directions. So impurities, if they are present in a metal, they introduce a new parameter, which is called mean free time. Mean free time. It tells you how long an electron can propagate before it gets scattered, on average. Mean is on average. Or you can also talk about L, which is mean free path. It's the same thing, how far the electron can travel before it gets scattered. And this mean free path actually is more or less, very crudely, it's like a distance between impurities. Electron flies freely along a straight line for the length L, and then it gets scattered. Then it flies freely again, and another L, and it gets scattered again. So L is like a distance. You can think of it as a distance between impurities. And these two things are related, of course. The more impurities you have, the less is the mean free path, and the less is the mean free time. So the mean free path is Fermi velocity times the mean free time. And Fermi velocity is the velocity of electrons at the Fermi energy. So if you take the electrons here, at this energy, they have a certain velocity. Fermi velocity is just Fermi momentum divided by the mass. Now, the question. Imagine these electrons are just like small points that move the way they move according to laws of usual classical mechanics, and they scatter on some obstacles with these parameters. What would be the diffusion constant of such a system? Actually, this problem can be solved on an elementary level. You just study how these particles scatter, propagate, and how the density change. So it's easy. It's written in some textbooks. I have read it myself 20 years ago, but I forgot how they do it. I just remember the answer. The answer is velocity squared times tau divided by d, which is 1, 2, or 3. And this is quite obvious. The faster they move, the better, the faster they diffuse. Yeah, and the more impurities you have, the star gets smaller, the diffusion is harder, because you have to overcome all these obstacles. And the exact number d here and the exact square, I forgot how it's done, but if you like, it's even by dimension, it should be like this. So, in this simplest model of a metal, we have a diffusion constant embedded there, and we will do another very important assumption. Namely, the Fermi momentum is large compared to the mean free time. Fermi momentum times mean free path is large, and the same is true for the Fermi energy. Fermi energy times the mean free time is also large, but large compared to what? H bar. Large compared to the Planck's constant. So this is a very important assumption that we will make. And we can formulate the same assumption in a different way. We assume the Planck's constant to be much smaller than everything. We can even put it equal to 0. And if Planck's constant is 0, it means we have no quantum mechanics, we have only classical mechanics. So this assumption actually means that our metal behaves like a classical metal, and quantum effects are weak and in some sense not important or negligibly small. So this thing is called semi-classical limit. Semi-classical limit. Why semi-classical, I have no idea. And also, in whatever I write here, I always assume that H is actually 1, so I often just say P Fermi much larger than 1. This is the same. For example, I believe I did a Fourier transform with omega and q without putting H there. But anyway, yeah, this is another assumption. Now, within this model, when we have impurities with this diffusion and this semi-classical limit, with this relation for chemical potential and for the density, we can use the Einstein relation to derive what the actual conductivity is. And in order to do this, we need nu here, nu. Let's compute the ratio. What is nu divided by n? Just out of, yeah.
I'm just thinking about this, just to understand. So here, when we have impurities, we don't consider electron and electron scattering.
No, we don't.
So we assume that they somehow don't kill each other, or how?
Yeah, this is exactly. This is the most simple model of a metal. In this model, electrons do not interact with each other. The only way they feel each other is the Pauli principle. They cannot occupy the same state. In this sense, they do feel each other. But once they occupy the state which no other electron occupies, then they move like a free particle.
Zero temperature.
Yes.
If we consider this as zero temperature, why wouldn't they just stay in their places and so on?
Because of the Pauli principle. They cannot stay, because stay means having zero momentum, and all electrons cannot have zero momentum. They still have, so we have states with finite momentum, and all these electrons do move even at zero temperature. What they do not do at zero temperature, they do not have a net current, so they all move in different directions, so the total current is zero, but if you apply electric field at zero temperature, you will still have a finite current. So you will still have a finite conductivity. Of course, in reality, temperature is not zero, but you should compare temperature to the Fermi energy. And in usual metals, Fermi energy is very large. Even at room temperature, it's often a good approximation to say that temperature is like zero. Fermi energy in metals I believe, is comparable to the temperature of the melting of this metal.
Do you need to add finite temperature? Because like otherwise you can't really use the scattering mode.
No. I can do it at 0 temperature. Actually, this is exactly my
Like if
answer.
you have like a lambda, like let's say you have like a Fermi sea, right? If you want to scatter, if you want an electron to scatter, right? You need another one to, like an electron will have to go to an unoccupied
Yeah.
state, right?
So you're right. 0 temperature means the equilibrium state at the lowest energy. All occupied states are occupied, all empty states are empty, and you cannot excite an electron. To excite an electron, you need an extra energy. But you excite an electron not with heat in the sample, not with temperature. You excite it with the external electric field. If you have external electric field, your system is out of equilibrium,
Yeah, no.
and you don't need temperature to
Yeah,
apply
I
the current.
understand. Okay, so when I was looking at this type of relation, like I know how you could derive the conductivity from it, but and then you could connect conductivity to fusion, right? But,
Yeah.
Could you directly calculate the fusion?
Yes.
That's what I'm asking.
Actually,
That's weird to me, right?
why?
Because then, okay, I get it that like this is classical.
You should somehow take the system out of equilibrium. You either apply electric field or you add by hand an extra particle and then ask how it will diffuse. And this extra particle is out of equilibrium. It occupies some states slightly above the Fermi.
Okay, thanks.
Okay, so simple arithmetical exercise. Nu divided by n equals. Nu is the derivative dn by d mu. So this is 1 over n times dn by d mu. Or the derivative of the logarithm of n by mu. Yeah, derivative of the logarithm is inverse n. And the logarithm of n is d times the logarithm of Fermi momentum. It's d logarithm of Fermi momentum by, I'm sorry, this is very crude, but it works. And this is d divided by p Fermi, d p Fermi by d mu. And this is mu and p Fermi are related like this. So d mu by dp Fermi is p Fermi over m. So this is d divided by p Fermi times m divided by p Fermi. And I forgot what's the next step. That's all. This is the last. Now, conductivity, according to the Einstein relation, is E squared times nu times diffusion constant. So nu we take from here. We write times the density n and times this ratio. Times n times d m divided by p Fermi squared. This thing here is just nu. And then diffusion constant, which is this thing, v Fermi squared tau divided by d. And v Fermi is p Fermi over m. So, first of all, d cancels out. And p Fermi squared, we have m v Fermi squared, so this 1, 2, 3 things is inverse m. N, yeah. It's n e squared tau divided by m. this is called Drude conductivity. Drude conductivity. So this is for a very simple model when the electrons in metal have this parabolic spectrum and they just are filled up to a certain Fermi energy and have some constant mean-free time and the corresponding diffusion. And the Drude conductivity, actually this was derived before Einstein. It was sometime in the 19th century, and of course Einstein knew about this result. So when he has his relation, he knows what to compare with. So this is the particular case of the Einstein relation. It can be derived from there, but the Einstein relation is much more general. You can assume any type of spectrum, not actually parabolic. You can assume any type of scattering, not just this oversimplified model with the classical. Anything. You can even include quantum effects. You can forget about this semi-classical limit, which I didn't tell you how to use, and you will still have this identity. But the Drude conductivity is correct only for parabolic spectrum, for simple impurity scattering, and for classical metal without any quantum effects. And you can easily see from this equation that it's very limited because it has mass inside. What is mass? Electron mass tells you what the shape of this parabola is. It's the coefficient between E and E squared. In a real metal, you can have very complicated spectra with many bands, with a very complicated Fermi surface, with whatever you like. There is no single parameter mass for electron in the real metal. So whenever it appears in the answer, you already know that this is for the simplified model with a parabola. Also, the conductivity according to Drude is proportional to the total density. Total density is the number of all field states. You should count all the states from the bottom up to the Fermi energy. Einstein relation doesn't have any density. Instead, it has density of states, which is the derivative, how n changes with chemical potential. It knows only about how spectrum behaves near this energy, how the density changes when you change chemical potential. It doesn't care about all these field states deep inside, that these states do not participate in conductivity anyway. So the fact that the Drude conductivity contains the total density instead of density of states, and the electron mass, which is a weird thing, tells you that this is the correct answer, but for a very particular model. And whenever you have an equation which involves only the parameters relevant for the vicinity of the Fermi energy, and which do not care about the shape of the Fermi surface, whether it's a circle or whatever else, then you know this is a universal formula.
Sorry?
Yep.
Another question to ask before. So if we have wire, metallic wire with this current because of some electric field, assume that J is not equal to 0.
J is not equal to 0, yes.
And if J is not equal to 0, then Einstein relation doesn't hold, right?
No, it does, because in the usual wire, when you apply the electric field, you have the current, but the density is constant, actually, so you don't have a density gradient. These two things do not compensate. And Einstein relation was derived starting with the assumption, let's assume we have a density gradient and electric field such that the effect of the two compensate each other. It was the assumption which allowed us to relate D to sigma. It doesn't mean that in any situation in nature current is always 0. Of course, there are states where current is not 0.
Yeah, but just I'm confused that we derived from one setup when there is no current. Then we say, oh, sigma actually the same for another setup when there is current.
Let me put it once again in a simple, hopefully simple words. There are two contributions to current, one due to diffusion, the other one due to conductivity. This one appears when you have the gradient of electric potential, when you have electric field. This one appears when you have the gradient of density, which corresponds to the gradient of chemical potential. And there are two ways to look at the same situation. One way is to say the current is 0, this plus this is 0. The other way is to say electrochemical potential is constant. This plus this is 0. And these two statements should be actually the same statement. It's the statement that the system is in the equilibrium. You can look at it from two different perspectives. From a perspective of electrochemical potential, or from a perspective that two currents compensate each other. And since this is the same situation, which you described from two different perspectives, from identifying this and that, you see that the conductivity and the diffusion constant should be related. And this is the Einstein relation. It doesn't mean that in any situation in real nature, they are always compensated and that the current is always 0. Still have a non-equilibrium cases when the current is non-zero, when the electrochemical potential is not a constant, and when these two things do not compensate. But the relation between them, if it was derived for one case, it will stay for any case, because you see there is no electric field here or any extra force.
Because I thought that when you wrote this formula, you said that, oh, basically the electrons scatter, they diffuse, that's why they have diffusion coefficient, and if we have a current with this conductivity, which is expressed by diffusion coefficient, because conductivity is because of diffusion.
Yes, that's all correct. So what's the problem?
Okay, we can discuss.
Electrons do diffuse in a metal, and this leads to a current. But to induce the current, to push them so that they start diffusing, you need an electric field. They will not diffuse by themselves. Unless you have a gradient of, if you have a gradient of concentration, they will diffuse by themselves.
Yeah, but that's what I was considering, that there is diffusion, what we mean by diffusion, that there is a gradient of particles, because otherwise,
Yeah.
to mention diffusion.
Right?
And then there is this relation.
Okay.
And then we say, oh, we have a current without a gradient of particles and the same.
Look, I see the problem now. So when I started in the very beginning, I said current is diffusion times gradient of n. There was no this second term. But this was about particle current, any particle in any medium. Later, when we came to this point, I say now we study electrons. They are not just any particles, they are charged particles. So first of all, we will study the electric current, not the density current. We will insert E here. And the second thing, you can have the electrical current not only as an effect of diffusion of the gradient, but you can also induce it with the electric field. So for electric current of real electrons, you should add the contribution of electric conductivity.
Then G is not equal to 0 and G is not equal to
Of course, in a general case, when you have any gradient of n and you have any electric field, you can have any current, which equals to this sum.
The relation doesn't hold.
Then J equals this. Do you agree? Then I say, or rather Einstein says, let's assume the current is 0. It's an assumption. We
Yeah, but if we know that it's not 0, we consider wire where we know the current is not 0.
then you throw this wire out of the window and you take another wire where the current is 0 and say this wire does conform to my assumption.
I mean, these were just numbers, like conductivity is a number,
Yeah, but like
diffusion constant is a number.
I mean, because
So-
the derived property of conductivity from diffusion, assuming that Z equal to 0, and apply it in the case where Z not equal to 0.
We derived a relation between two numbers.
In principle,
Yeah,
like,
which is valid if J equal to 0, then you consider the case J not equal to 0.
So you are telling me that the conductivity changes.
Yeah, it's obvious that
Wait.
it's the same.
If I take a piece of metal and it's written 5 kilo ohm, I mean the resistor, and then I take another resistor, take this resistor and I pass the current through it, and then it's suddenly not 5 kilo ohm, it's now 10 kilo ohm, because the conductivity changes when you pass the current. Is this your statement?
Yeah, from this model it's not obvious that conductivity would be the same in the case of current, because we derived it.
I mean,
Sorry, I forgot to say, sorry. Before doing anything, we assume that the conductivity of the metal does not depend on the current flowing through it.
Well, it's a big assumption, which is I hope it's assumption.
I mean, it's a good assumption if the current is small.
You have a personal homework. Next time you will give me an example when the conductivity does depend on the current and explain why.
I mean, it can. You
Because-
can have, like, it's
because
a
I really don't know
problem.
such examples.
At some point it will not. That's for sure.
Okay,
But like,
right.
But we're in the linear.
It's in the linear regime. You have small gradient, small electric field, small current, and the coefficient is the constant which does not depend on the applied field. This is true.
if nothing else, like at some point it will go down. If you pass current through it, it will not.
Yeah, actually correct. Yeah, I relieve you from the homework. I already got the answer. Right, if you pass a very high current, of course you can melt your metal and then it will not conduct anymore. So the random linear effects, that's true.
I have a question. Like if you have so what if, this is probably going to be in later lectures or my country. So what if now you have localization, for example,
All of
to
this,
series, right?
this will be, yeah.
Well, that should bring the diffusion to zero, right?
Yes.
Because they shouldn't move at all.
Yes.
So there, this is the mean free path should be zero. Right?
No. Mean free path remains the same, but this relation between diffusion constant and mean free path is changed.
Okay.
Diffusion constant is zero, mean free path is not.
Great.
Yeah, and this hopefully will be just on the next lecture. Hopefully. Okay, very good. So where did I stop? Right here. Yeah, I believe it's probably enough for today. And the next lecture is when? Wednesday, in 2 days. And where?
It's written on the website of the course.
It's written on the website, I have no idea. But so I hope to see as many as possible